Deep beneath the mountains of Guizhou province in southwestern China, engineering teams faced an impossible challenge. They needed to drill through 18 kilometers of solid rock, crossing some of the most geologically unstable terrain on Earth, where mountains rise like shattered teeth and underground rivers flow through limestone caves that could swallow entire buildings. The region had defeated road builders for generations, but in the early 2000s, China committed to the unthinkable, boring the longest highway tunnel ever attempted through a mountain range so fractured that geologists warned it could collapse at any moment. This is the story of how Chinese engineers conquered the impossible, drilling through 18 kilometers of mountain to create a passage that would connect isolated communities and slash travel times from 5 hours to 15 minutes. What technologies allowed them to succeed where others feared to try? How do you prevent a mountain from crushing your tunnel while you're still digging it? Join us as we journey into the heart of the mountain, exploring one of the most audacious engineering projects of the 21st century. Guizhou province presents a landscape that seems designed to thwart human ambition. The region is known for its karst topography, a geological formation where limestone bedrock has been dissolved by water over millions of years, creating a maze of caves, sinkholes, and underground rivers. Above ground, the mountains rise in jagged peaks, some reaching over 2,000 meters in elevation. Between these peaks, valleys plunge down into shadows where sunlight barely penetrates. For centuries, the people living in these mountains were isolated, their communities accessible only by narrow roads that twisted through the peaks, routes so treacherous that a journey of 30 kilometers could take an entire day. The decision to build the tunnel came in 2008, part of China's massive infrastructure expansion to connect every corner of the nation. The tunnel would link the cities of Zunyi and Bijie, cutting through the heart of the Dalo Mountains. But this wasn't just about convenience. The existing mountain roads were death traps, claiming dozens of lives each year as vehicles plunged off cliffs or were buried by landslides. A tunnel would save lives, reduce travel time by 70%, and open economic opportunities for millions living in one of China's poorest regions. Before a single drill bit touched rock, survey teams spent over 2 years studying the mountain. They deployed ground-penetrating radar, drilled hundreds of exploratory boreholes, and conducted seismic surveys that sent shock waves through the earth to map underground structures. What they discovered was deeply troubling. The mountain wasn't a solid block of granite. Instead, it was a geological nightmare. Layers of limestone riddled with caves, fault lines cutting through the rock at unpredictable angles, and underground rivers that could flood a tunnel in minutes. In one exploratory borehole, drills broke through into a massive hidden cavern, a void large enough to park 50 buses. Conventional tunnel boring methods would never work here. Chinese engineers turned to a hybrid approach, combining tunnel boring machines with traditional drill and blast methods, switching techniques based on the geology they encountered meter by meter. The project would employ over 8,000 workers, consume 5 years of continuous 24-hour construction, and cost nearly 6 billion yuan, equivalent to almost $1 billion at the time. The challenges ahead would test the limits of modern engineering. The tunnel would have 2 parallel bores, each measuring 18.4 kilometers long, allowing traffic to flow in opposite directions. Each bore would be 10.5 meters wide and 8 meters tall, large enough to accommodate 3 lanes of highway traffic. The portals, the entrance and exit points were positioned carefully, with engineers selecting locations where the rock was most stable. Constructing the portals alone took 6 months, requiring the excavation of enormous trenches into the mountainside, reinforced with concrete walls 30 meters thick to prevent landslides. The tunnel boring machines, or TBMs, selected for this project were manufactured by China Railway Construction Heavy Industry Corporation, massive cylindrical devices measuring over 150 meters long and weighing over 2,000 tons each. At the front of each TBM, a circular cutting head measuring 10.5 meters in diameter bristled with over 300 disc cutters, each made from hardened steel designed to grind through solid rock. The cutting head rotated at approximately 5 revolutions per minute, pressing against the rock face with forces exceeding 5,000 tons. As the cutting head chewed through rock, it created chips and dust that were mixed with water to form a slurry which was pumped backward through the TBM and out of the tunnel. Behind the cutting head, hydraulic jacks pushed the entire machine forward, advancing approximately 40 millimeters with each revolution. This might sound slow, but under ideal conditions, a TBM could advance up to 25 meters per day, essentially boring through the length of a large house miles every 24 hours, but conditions were rarely ideal. Within the first kilometer, the lead TBM encountered its first major crisis, a fault zone, an area where ancient geological forces had shattered the rock into fragments. Drilling through a fault zone is like trying to dig through a pile of bricks with nothing holding them together. As the TBM advanced, rock fell from the ceiling, jamming the cutters and threatening to bury the machine. Work halted immediately. Engineers pumped quick-setting cement grout into the fractured rock ahead of the TBM, essentially gluing the broken mountain back together before proceeding. This single fault zone delayed the project by 3 months. The deeper they bored, the more challenges emerged. At kilometer 4, the TBM suddenly lurched downward as the cutting head broke through into a hidden cave. Water began pouring in, flooding the tunnel at a rate of 300 liters per second. Emergency pumps were deployed, but the source needed to be sealed. Engineers drilled dozens of holes around the cave opening, injecting special expanding foam and cement grout that solidified on contact with water, eventually plugging the breach. But not before over 2 million liters of water had flooded into the tunnel, requiring weeks to pump out and dry. Temperature inside the tunnel presented another brutal challenge. At shallow depths, the rock temperature was bearable, but as the tunnel bored deeper beneath the mountain, the ambient temperature climbed steadily. By kilometer 9, at the deepest point over 800 meters beneath the mountain peak, the rock temperature exceeded 45 degrees Celsius. Workers labored in conditions approaching 50 degrees with humidity near 100%. The heat came from geothermal energy, the natural warmth of the Earth's interior. To make conditions survivable, engineers installed massive ventilation systems, including ducts measuring 2 meters in diameter that channeled fresh air from the surface. Industrial air conditioning units cooled the incoming air, while enormous fans pushed hot, stale air out. Even with these systems, workers could only labor in 30-minute shifts before requiring rest and rehydration. Supporting the tunnel as it was excavated required immediate action. In stable rock, the TBM's own structure provided temporary support, but the machine was always moving forward, and the tunnel it left behind needed permanent reinforcement. Chinese engineers employed a technique called shotcrete lining, where a mixture of concrete, steel fibers, and additives was sprayed onto the freshly excavated rock surface at high velocity. The shotcrete formed a protective skin, hardening within minutes to prevent rock falls. This initial layer was typically 10 centimeters thick. Behind the shotcrete crews came the steel arch installers, positioning enormous curved steel beams that formed rings around the tunnel circumference. These lattice girders, each weighing over 2 tons, were positioned every meter along the tunnel length, creating a cage of steel that held back the mountain. Finally, a permanent concrete lining, 40 centimeters thick and reinforced with steel rebar, was poured between the rock wall and steel arches, creating a permanent structure rated to withstand the immense pressure of the mountain above. But the karst geology delivered its worst surprise at kilometer 12. As the TBM advanced, instruments detected a massive void ahead, a limestone cavern over 70 meters tall and 300 meters long. The tunnel route passed directly through it. The engineering team faced a terrible choice: reroute the tunnel, adding months and massive costs, or engineer a solution to cross the void. They chose to fight. The plan was audacious. They would build a massive concrete tube through the center of the cavern, essentially constructing a bridge suspended in open air inside the mountain. First, they carefully excavated to expose the cavern, then installed enormous steel scaffolding structures rising from the cavern floor to support formwork for the concrete tube. The tube itself was reinforced with steel cages containing bars as thick as a human arm, designed to be self-supporting even if the cavern rock around it shifted or collapsed. Pouring the concrete required bringing in specialized pumps capable of lifting concrete over 100 meters vertically. The entire operation took 7 months, and when complete, the concrete tube weighed over 40,000 tons, a prosend bridge to nowhere hidden inside a mountain. Water management throughout the tunnel was a constant battle. The limestone rock was like a sponge, saturated with groundwater that seeped through every crack and fissure. In some sections, water flowed from the walls at rates exceeding 500 liters per second, second, enough to fill an Olympic swimming pool in less than 2 hours. Engineers installed extensive drainage systems, perforated pipes embedded behind the tunnel lining, collected groundwater, and channeled it to collection sumps where massive pumps lifted it to the surface. In total, the tunnel's drainage system included over 30 kilometers of pipes and 60 heavy-duty pumps operating continuously. Communication and safety systems installed throughout the tunnel were equally sophisticated. Fiber optic cables ran the entire 18-kilometer length, providing high-speed data connections for monitoring systems. Over 3,000 sensors continuously measured air quality, temperature, structural stress, and water seepage. Emergency refuge chambers, reinforced concrete rooms stocked with oxygen, food, and water, were positioned every 500 meters, providing safe havens if disaster struck. Fire suppression systems included water mist generators that could fill the tunnel with ultra-fine water droplets, suffocating fires while using minimal water. Ventilation for the completed tunnel required engineering on a massive scale. With 18 kilometers of enclosed space, vehicle exhaust would quickly create toxic conditions without proper air circulation. Chinese engineers designed a system with 4 massive ventilation shafts drilled vertically through the mountain at strategic points along the tunnel route. Each shaft measured 8 meters in diameter and descended up to 600 meters to intersect the tunnel. At the surface, enormous fan installations, each powered by motors generating over 1,000 kilowatts, forced fresh air down into the tunnel. The ventilation system completely refreshes in both tunnel bores every 5 minutes, requiring over 2 million cubic meters of air movement per hour. Lighting the tunnel presented unique challenges. Traditional overhead lights would create harsh shadows and driver fatigue over such a long distance. Instead, engineers installed LED strip lighting along both walls at regular intervals, creating a soft, even illumination that reduces eye strain. The lighting system includes over 50,000 individual LED fixtures, consuming less power than traditional lights while providing superior visibility. Additionally, the tunnel features adaptive lighting that gradually transitions from bright daylight levels at the portals to lower interior lighting, helping drivers' eyes adjust and reducing accident risk. The breakthrough moment came in August of 2013, when the 2 TBMs, one boring from each end, finally met in the middle of the mountain. The alignment was extraordinary. After drilling 18 kilometers through fractured rock, crossing fault zones, and navigating around underground rivers, the 2 bores met with less than 50 millimeters of deviation, an accuracy that defied belief. When workers broke through the final rock barrier, crews from both sides shook hands through the opening, a celebration of one of the greatest precision engineering achievements in modern history. But completing the bore was only half the battle. The final 2 years were spent completing the permanent lining, installing all safety and operational systems, paving the roadway, and conducting exhaustive testing. Every centimeter of the tunnel was inspected, every weld examined, every system tested under simulated emergency conditions. Fire drills, evacuation procedures, and traffic management protocols were rehearsed hundreds of times. The completed tunnel opened to traffic in November of 2015. On opening day, thousands of local residents walked through the tunnel before vehicles were allowed, marveling at the passage that had transformed their isolated region. The economic impact was immediate and profound. Travel time between Zunyi and Beiji dropped from over 5 hours to 30 minutes. Businesses that had struggled with transportation costs suddenly had access to larger markets. Agricultural products from the region could reach cities while still fresh. Tourism began to flow into an area that had been too difficult to access. The tunnel's cost per meter exceeded $50,000, making it one of the most expensive tunnels ever built, but the value it created immeasurably exceeded the investment. It connected communities, saved lives by eliminating treacherous mountain roads, and proved that even the most challenging geography could be overcome with determination and advanced engineering. From the first exploratory boreholes to the moment vehicles first drove through the mountain, every step represented the cutting edge of tunnel engineering. The project pushed Chinese engineers to develop new techniques for dealing with karst geology, techniques now used in tunneling projects worldwide. The mountain that had isolated communities for centuries was finally conquered, not with explosives and brute force, but with precision, patience, and extraordinary engineering that turned an impossible dream into a passage through solid rock.